So thanks SIGA and World Bank for coordinating and inviting me to give a little talk. So I'm an assistant professor at UC Berkeley in the School of Information. The School of Information is sort of this hybrid economics, computer science department. And I'll sort of start with a quote from a column by Sendhil Mullainathan in the New York Times, which I think is sort of relevant to what I'm going to talk about, but also for this conference in general. And just reading it, he says, "Why should the financial services industry, where mere dollars are at stake, be using more advanced technologies than the aid industry, where human life is at stake?" And he wrote this in New York. I think if he were writing this from San Francisco, he'd probably have said something about internet. But I think this is sort of part of the idea behind this conference and this emerging field is that there's all this low-hanging fruit. And a lot of what's being done right now is taking these tools that were designed to target advertisements and place products and predict option values and so forth, and just applying them in a different context, to the context that affects actually the vast majority of the world's population. And so, I have only 15 minutes or so, relatively modest goals. I'll try and, if you need convincing, convince you that there's a lot of exciting work to be done here, sort of at this intersection between AI, and I think Tom hit it on the head, in particular this subfield of AI that's supervised machine learning, and then development and global poverty. And I'll do that instead of sort of doing a broad overview by doing the best I can to do a deep dive, although it'll be sort of shallow since there's only a few minutes, to try and tease apart how, on the one hand, there's these really low-hanging fruit and so the study I'll talk about is a very simple study about basic measurement. It's not really, there's nothing really complex going on. We're not inventing any new supervised learning algorithms. But it'll also highlight some of the more thorny challenges in the sense that you can't just take stuff off the shelf. It requires a little bit of engineering insight to figure out how to apply them in a different context. Okay, so a little bit of level setting. I think particularly in a building like this, it's easy to sort of get lulled into the sense that big data is everywhere. It's it's making this room work. It's coming from all of our devices. The numbers are fairly astounding, but I'll just briefly make the point that this is actually more the exception than the norm. Most of the world is living in a much more data scarce environment. And if you can see the table, I apologize, it's pretty small. These numbers are just indicating the number of years it's been since the last census was conducted in a few cherry-picked developing countries. And to give you a little bit of context for what these numbers mean, you can see, or if you can see, the numbers at the bottom of the screen, just show how much a population changes when 40 years elapse between successive censuses. And so in Angola, between 1970 and 2014, the population grew from 5.6 million to 24.4 million, so a 350% population growth. Not to mention this devastating internal civil war, mass migration, both internal and international. And so, not just for social science researchers like me and for companies like Google that are trying to explore new markets, but in particular for people at the World Bank and policymakers in the country that are trying to figure out what policies to design and how to target them in these countries, these data gaps are really insidious. And towards the end of the talk, I'll mention a few specific examples of how I think filling in these quantitative gaps can be pretty useful. So the question that I'll sort of do this shallow deep dive into is asking, can we take the new sources of data that are coming from developing countries and sort of combine them with some of these novel advances in AI, although some of these advances aren't so recent. And the specific question I'm going to ask about, and I think a few of the other talks today will touch on similar question, but is just about basic measurement of poverty, wealth, human development, and vulnerability. And just to sort of explain what you're seeing in front of you, the data set on your left is showing 1 day of mobile phone activity in Afghanistan. The data set on the right is showing a day in the life of Beijing using sort of the equivalent data coming from the equivalent of Google Maps in China. And so, I mentioned it at the beginning, and Tom alluded to this as well. The problem is for the average computer scientist or AI researcher who's used to just grabbing data from Twitter or LinkedIn or Yelp or what have you, those social media data sources are, at this point, very underutilized in developing countries. Rates of penetration at the top end are maybe like 10%. But again, as Tom alluded to, the two exceptions that are and this will be a common thread you'll see in a lot of the talks today, are phone data and satellite data. And with phones, there's billions of poor people using mobile phones. Sort of the median sub-Saharan African country, even they have roughly 50% penetration. In some developing countries, it's much, much higher. Afghanistan, where I do a lot of work, it's more like 75%. And then the other technology is remote sensing, satellite data. And here the technology is getting better by the month. I mean, companies in San Francisco are now imaging every populated point on the Earth's planet every day. The resolution of the images you get are getting finer and finer. So this is really opening up a lot of interesting possibilities. Okay, but the one thing I'll talk about a little bit, and this is actually joint work with Gabe, who's in the room somewhere in the red shirt, and Robert, who I don't think is here yet, but will be here today, so you can ask them about the details, is to, in the words of Tom, just create a labeled training set. So these supervised machine learning algorithms really, to flourish, need to have data where you have input and output, where the input and the output are known. So I'll talk more what I mean about that in a second. But the data we're going to use is phone data that comes from the mobile phone operator in Rwanda. And the key insight, or the key thing that enabled us to do this study, was to match data coming from mobile phone operators to data that we collected in surveys. So the basic idea is that for some people in this large database of 1.5 million phone subscribers, we actually match the anonymized data on how they're using their phones to data that we collect in surveys, where we talk to them, in this case on the phone, and other studies in person. So that allows us to connect the sort of anonymized data with data about actual quality of life for the experienced by these individuals. And at that point, we can sort of take a lot of the tools in machine learning and try and answer this question of A, can we understand what the signals of poverty are in the phone data? And then B, can we use it to fill some of these data gaps about not understanding where poverty is and how extreme it is? Okay, so I'll go just a little bit deeper into the methods. It'll still be fairly superficial, but the basic idea, and this is sort of the standard recipe you'll see in a lot of the talks today and a lot of the work that's being done in this field, is to first go from your sort of novel digital data set. And in this case, it's terabytes of log data that just describe the phone calls made by people, the text messages sent by people. So basically have billions of entries that look more or less like this, where you see the ID of the person making the call, the ID of the person receiving the call, metadata about the call, like the time of the call and the locations of the cell towers that the call was routed through, and then just gobs and gobs of data like this. And then with feature engineering, which will come up again and again, the idea is to take that raw data and convert it into metrics that can be used for interpretation and for downstream analysis. So the downstream analysis we want to do is to predict wealth and poverty, to look at the phone data and say who in this data set is rich and who in this data set is poor. And so, if I had more time, I'd ask you guys to brainstorm about what aspects of mobile phone use you think would be the best predictors of poverty. And the things that people tend to come up with are like total expenditures on airtime, or number of international calls, or, your ingenuity is sort of the limit on how to solve this problem. The solution we use, and it's by no means the right solution, and this is sort of just an example of how this is really just at the cusp of this field. There's this field of feature engineering is very underdeveloped, and particularly as it relates to developing country context, it's very under-researched. So we developed one method that transforms the original log data into order 5,000 of metrics like this that have some real-world interpretation, but I'll argue, and you'll see in a second, aren't the sort of things that you would probably naturally come up with. Some of them are, but then there's thousands of them that are sort of weird permutations of things that make sense. But then we have this, for each person, we have thousands of metrics that describe their phone use. And then this sort of leads to the common challenge in a supervised learning problem, which is to say, how can the computer learn the relationship between those characteristics of the people? So those are the X variables here, the predictor variables, and then the thing that we're trying to predict, or the Y variable. In this case, Y is what we collect in the survey. So in this particular study in Rwanda, there were 856 people that participated in the survey. For those 856 people, we have these thousands of metrics that describe their phone use, and then we have information collected in the survey. And for all intents and purposes, the details don't matter too much. what we do is we take answers to several questions in the survey that we know are correlated with wealth. Things like whether you own a motorcycle or a radio or a TV, or whether your roof is made of tin or of thatched, and so forth. And we collapse them into a single index that gives us a quote-unquote ground truth measure of the wealth or poverty of the person who's using that particular phone. Now, there's a lot of details there, and that measure of wealth or poverty is noisy in itself. And that's sort of one of the challenges here, is that even when you have a supervised learning problem, the thing that you're considering ground truth is not truth. It's just some reflection of what the people report in the surveys. And that's a whole other topic that is ripe for innovation. But then how do we actually do this? And so this is like the first slide of the first class in the course I teach on machine learning. And I think it's a really useful diagram for people that, the 10% of people in the room that aren't familiar with machine learning. This is from a guy at University of Washington named Pedro Domingos. It sort of contrasts the traditional programming paradigm, which is, you have a bunch of data, you write a computer program to manipulate that data, you feed both of those into the computer, and on the other end you get some output. And 95% of computer programs, engineering code out there looks more or less like this. But what machine learning does is sort of flips it around a little and says, okay, instead of feeding the computer the data in the program, I want to feed the computer the data and the output. And the role of the computer and the role of the algorithm is to tell us what the program is that functionally maps the input to the output. Right? So in our particular example, what I want to do is I want to use machine learning to predict poverty from phone data. And so in this diagram, the data we're putting in is those characteristics of phone use. The data we want to come out is measures of poverty. And again, the poverty is coming from the survey. The phone data is coming from the phone company. And on the other end, we get this functional mapping that maps the x's to the y's. And that F is the model. And once you have the model, you can do cool stuff like figure out which metrics of those 5,000 that we derive are actually predictive of wealth and poverty. And then importantly, you can start to use it for prediction. So given those 5,000 metrics, in other words, any one of the 1.5 million people that use their phones in Rwanda for whom we have those 5,000 metrics, we can give our best guess, a prediction of their poverty based on this model. And so what does it actually look like in practice? This is what I alluded to earlier. So if you look at which of those 5,000 metrics in Rwanda amongst this population of 856 phone users are most predictive of poverty, well, the things that I was sort of mentioning earlier, like total spend on airtime and total number of international calls, they are correlated with the wealth of the subscriber. But the things that are most correlated with the subscriber are these fairly obscure characteristics of phone use. So how much time do I have?
7 minutes.
7 minutes? OK, so I'll just tell you what the first one is. So there's this one feature. Your guess is as good as mine, and we could sort of armchair philosophize about why this is the case. But the single best predictor of wealth in Rwanda is the following. It's the weighted average of the first-degree neighbor's day-of-week entropy of outgoing SMS volume. So what that means is we just look at the outgoing SMSs. So the SMSs sent by a person, and then we take the day-of-week entropy. In other words, we divide that into a bin, a distribution with 7 bins, one for each day. So we count the number of outgoing SMSs made on each day of the week, and then we take the entropy of that distribution, which gives us some sense of the variation or the predictability of that distribution. And then if I want to predict how wealthy Tom is, I don't look at Tom's outgoing SMS day-of-week entropy. I look at all the people that Tom has spoken to on the phone network, and I look at their outgoing SMS entropy and weight that average by the amount Tom talks to those people. So the point is, these are sort of things that maybe we could weave a story about why they're predictive of wealth, but just empirically we find they are. And again, I sort of leave this more as an example of how much room there is to still do more useful work, because this is pretty silly. The other thing we do, once we fit these models, is, and what I'll focus on for the next 2 minutes, is to say, OK, once we have this model that maps our x's to our y's, and the model is learned on this population of 856 people, let's go then apply this model to a bunch of other people. So in the case of Rwanda, what this is showing you is for the 856 people in the survey, each of the people is a dot. This is plotting the predicted wealth of the person against the actual wealth of the person. The predictions coming from this algorithm, the actual wealth is coming from the survey. But then once we've trained that algorithm, we can do these out-of-sample predictions and say, OK, for the 1.5 million people in Rwanda who use their phones, who exist in the X data set, but who don't exist in the Y data set because we didn't have the resources to actually call them or visit them and figure out how wealthy they are. Let's just predict what their wealth looks like, and then let's plot it on a map where we can assign locations roughly based on the locations we see them using their phone from. So you get this very granular map of predicted wealth in Rwanda. You can start to aggregate it. This is showing you the predicted distribution of wealth based on the phone use of people according to the 2,100 administrative cells in the country. And why this is useful, sort of, one is to have maps like this. And not just is there, as I started out by pointing out the lag between successive surveys. Another constraint when you're doing surveys is being able to get granular maps of wealth that allow you to do things like targeting. So if you went to the National Institute of Statistics in Rwanda and asked them for a map of the distribution of wealth, they'd give you something like this on the right-hand side. Because the publicly available data in Rwanda, the lowest level of spatial aggregation at which it's accurate is at the district level. They don't have maps like this. But what we can do is we can compare the maps we have when aggregated to the maps you're getting from the National Institute of Statistics. And what we find is that they're not perfect, but that the maps we generate are roughly as accurate as the map from 5 years ago from the National Institute of Statistics. And so this sort of brings me to where I'll close these brief remarks, is to sort of try and answer this question. Okay, how is this actually useful? Like, there's this clever exercise where we're using machine learning and we're collecting a lot of data and producing cool videos, but what are the actual applications? And so the one I started with is this. And by no means, and sometimes this is like a takeaway that I don't want to come from talks like this, I'm not at any level arguing that big data and these sort of fancy algorithms should replace traditional methods for data collection, survey-based data collection, and so forth. That sort of data is much more robust. It's much better understood, the sources of measurement error, and so forth. But in a lot of cases, and Rwanda is not one of them, but in a lot of cases, it's been 30 years since you've had a census or a nationally representative survey. So if you need something, if you don't have the $15 million it costs to conduct a nationally representative household survey, or the $10 billion it costs to conduct a census, then these are a cheap and sort of effective solution. Again, it's not perfectly accurate. There's plenty of error, but it's much faster and much cheaper. Another application, and this is where I really think, sort of speaking to Tom's point about identifying a few killer apps. I think this is going to be, in my mind, the killer app for phone data, at least, is to use these sort of methods not to say something about the levels or the cross-sectional distribution of human development, but to say something about changes over time. And the advantage of phone data is that it's updated very, very frequently. And so naively, you might say, okay, let's just take that model that we trained in 2009, using data from 2009 in Rwanda, and update the data in 2010 and 2011, and then we'll have updated maps. And that's true, and again, this is a totally under-researched area in this field, is we have no idea how accurate those maps would be at a different point in time than when they're trained. There is a branch of computer science on this, in active learning and so forth, but to date, no one's really applied those methods to these sort of problems. But if you could solve that problem, if you could get updated real-time estimates of the distribution of wealth and poverty from phone data or from satellite data, there's all sorts of really cool applications, and cool in a really meaningful, not a trivial sense. One is thinking about targeting resources, just understanding who's poor, who's not, and figuring out how to get the people that really need the resources, instead of the people that somehow make you think that they need the resources, getting the resources. I think Dan will talk a little bit about this a little bit later today. Another compelling application is crisis response, and this will be the last video I show you. But what I'm going to show you is the same data we used for the study that I was talking about in Rwanda to do wealth prediction, but just a different spin on the data. So what I'm going to show you is data from the same network in Rwanda on the day of an earthquake. So this is February 3rd, 2008. The epicenter, here's the USGS report on the earthquake. You can see where the epicenter is. And this is an animation of call traffic on the day of the earthquake. And right now it's pretty noisy. And if you can see this ticker at the top, this means it's 3 a.m. Each frame in this video is 1 minute of call activity in Rwanda. And the cell tower, the country is divided into polygons where each polygon represents a cell phone tower. And red means there's a lot of incoming calls, and blue means there's not a lot. And it's still noisy until the earthquake strikes. And so it just happened. As soon as the earthquake happens, you see all of the calls get concentrated into the region of the country affected by the earthquake. And so the question is, can you use this to sort of do improved disaster crisis response to target resources, again, much more timely fashion than would be possible with traditional means. And the last application that I'll talk about, and again, this is really what I think truly is the killer app, is to think about new approaches to impact evaluation. Because a critical constraint to doing quantitative impact evaluation is having data about the state of the population before the intervention and after the intervention, or before the policy and after the policy. But if you could get reliable data for free from a mobile phone network, then you can start to think about how causal attribution of the changes you observe in welfare in the population. And we have some preliminary work here, but again, this is totally open area for research. But it looks like there's signal, right? So what I'm showing you on this graph here is for a population of 1,200 Afghan citizens. I'm showing you how one of those 5,000 metrics of phone use is changing in response to 25, 30 different shocks that are experienced by these people. So we know whether they experience these shocks through a series of panel surveys with the respondents. And if you look at this closely, you can see these two top shocks, these cash drops, the large and small cash drops, those are randomized cash transfers that we've given to these respondents. And what we see is after these respondents receive an unexpected windfall of income, that they actually stop making phone calls. And there's a different graph like this for all of the 5,000 metrics of phone use. And the question is, clearly there's some signal here. What's going on? We don't really understand, but just like before, we can throw all of that signal into a predictive model. And it turns out when we do that, we can actually fairly accurately predict which people in the sample are receiving these positive windfalls. Now this is just the beginning, right? That we're still a long way from being able to predict more nuanced changes in welfare and happiness and subjective well-being experienced by these respondents, but clearly there's information in this data that should allow us to do so. So again, maybe just to close, I think there's a ton of potential for using these new sources of data, new computer algorithms, machine learning and artificial intelligence to understand some of these fundamental questions about the causes and consequences of poverty. I've talked really just about this one issue of measuring poverty, the sort of the most basic starting point here. But these and other areas, some of which Tom alluded to, I think are really ripe for research and innovation. So again, the two takeaways, I think hopefully you're maybe marginally more convinced that there's a lot of interesting work to be done here.
They've done a Bayesian update.
Hopefully you've done a Bayesian update. And in particular, there's sort of room across the spectrum. If you really just want to tackle the low-hanging fruit and you don't have the technical chops, there's a lot of work to be done for people that have like the right development intuition about sort of the local context. On the other end of the spectrum, there's some really thick, thorny technical challenges. If you really just want to publish CS theory papers and CS conferences, there's still a lot of interesting work to be done. Okay, sorry for talking so fast, but I think I made it in time. Thanks.